I was going to celebrate today because I was feeling like we were going to do it. Riemann sum. What is a Riemann sum? It's a way to estimate the area under the curve using what? What do you use? Rectangles. You use what? We don't call trapezoid a Riemann sum. It's got its own name. It's called trapezoidal rule. Okay? Riemann sum is using rectangles. So summation notation. It's a compact way to write Riemann sums into a single expression. This lesson will lay the foundation for the definition of the definite integral. While you may have seen sigma notation, in an earlier course like AP Stats, or if you've had Mr. Morris ever and seen him as a teacher, we will focus on using this tool to write Riemann sums. Nobody's smiling. Everybody's like, it's dumb, Mr. Morris. All right, understanding summation notation. All right, summation notation is a method for summing up a finite number of terms in a sequence. So it's a compact way to write out how many Riemann sums you want to do. Like if you're estimating using 6 rectangles or 5 rectangles or 4 rectangles. The Greek letter sigma is known as the operator, and sigma just means find the sum. Everybody, sigma means find the sum. Okay, and it indicates this process. Now, all you're required to do, Blake, on the ACT is be able to take it from sigma notation to an integral or from integral notation back to sigma. Did you see one on the 1997? It would have been in the very end.
Where's this at the ACT?
AP exam. Yeah. Did you see one at the, because I did ACT prep this morning. Did you see one at the end? Was there one on the 1997? I can't remember. It was like,
guessing at the end.
It's fine.
I saw it and I was.
Yeah, you might have guessed on it. It had the sigma notation. I know not one of them does have it. I think you're saying we did have one. Okay, so you'll know how to do it after today. Okay, so next time we do the 1998, you'll get it. And it's not hard to do. It's just looking at it, recognizing what everything means is all you got to be able to do. So first of all, you've got the summation notation sign, which is the sigma. You've got the index of summation. This is where you start. We always start with k equals 1, but on Friday you did see that you could start at other k values. Okay? And the reason we start at k equals 1 because we're starting, when you count, you start with what number? 1. Because we're counting the number of rectangles. The first rectangle, the second rectangle, the third rectangle, the fourth rectangles. If y'all need to lower that, you can. Okay? Maybe you do want to keep it up because tomorrow and Wednesday it's not going to look like this out there. Okay? K equals 1, k equals 2, k equals 3, k equals 4. Okay? It's probably going to happen Wednesday, and I'm going to Zoom Wednesday if it does. I'm going to. I'm going to have to.
Yeah, can we do a group FaceTime?
Yeah, we can do a group FaceTime. That's fine. Okay? I have to. We cannot miss any more minutes. We can't afford. Shh, quiet. Don't get distracted. If school gets canceled one day, I'm going to have a live session. Shh, shh, shh. Here we go. Yeah, I'll tell you what time. The day tomorrow. If we looks like it's going to miss Wednesday, I'll give you a time for Wednesday because you're all going to be sitting your butts at home anyways. Okay? All right. Shh. All right, so k equals 1. That's my start. I'm going to start with the first rectangle. I'm going to go to the nth rectangle. Now, this is the number of rectangles you want to do. It's called the upper limit or the stopping point. Okay? So if you did 6 rectangles, you'll go from 1 to 6. If you did 7 rectangles, it'll go from 1 to 7. They can switch it on you. If they started at 0 and you did 6 rectangles, it wouldn't go from 1 to 6. It'd go from 0 to what? 5. And they have been known to do that on the AP exam. To shift it over and start it at 0 and know that you would have to go from 0 to 5 because 0 would be your first rectangle. And then 1 would be your second rectangle. And 2 would be your third rectangle. Up to 5 being your sixth rectangle. So if they do start it at 0, notice that 0 is starting with your first rectangle. You're using 0 as the starting point. They don't do it often, but they could. They could just trick you and move it over 1. Okay? All right. So, and we went, and then the expression, x to the k power is the expression. We showed how to plug this in. For those of you who weren't here, watch the video from Friday. It's not too super complicated. Now, what we're going to look at is it's acceptable to use any letter for the index of summation. We just use k. But they might use something else. They might use I. I have seen them use I equals 1. It doesn't matter what they use here. The only thing they typically won't use is n, because n will be the upper limit. Okay, they'll always do n for the upper limit, because they'll say n equals 4, which means do 4 rectangles, or n equals 5, which means do 5 rectangles, or n equals 10, which means do 10 rectangles. Okay? But this right here, they'll use, I've seen them use J, I, K, L, M, N, O, not N, L, M, O, P. Yeah, you know me. Okay? So they might use some other things. All right? So they might use, but most textbooks uses, my wife was teasing me about that the other day, because she has a hard time sometimes talking really fast and her words get jumbled up. And I said, every now and then I do. And she was like, yes, you do. All right, I, K, and N. Be aware that some summation expressions have other variables. For example, notice that we have got K's, but we also have X's. X is the variable of your equation, of your expression. It's probably going to be the equation that we're finding the area under. Okay? So in this problem, it looks like we're doing the area of some, parabola to the 2k minus 1 power. Okay? Or it could be other things. It doesn't have to be a parabola. Actually, you got a J-curve here. Okay? This will help us understand how summation notation represents Riemann sums for a function. And we're going to have our x of I notation. And we talked about this is going to be the ith rectangle. The first rectangle, the second rectangle, the third rectangle, the ith rectangle. And this is actually going to be the height, because remember, when you plug the x into the function, that's the height of the function, which is going to be the height of the rectangle. And then we're going to have our width, delta x, which brings me to where we were at. And I need to go back to this, because go back to page, just scroll back to page 331. Here was the notation we were given at first. Okay? So for those of you who didn't see this from Friday, notice you got k equals 1 to n. N represents the number of rectangles. But if I let n approach infinity, now we're not doing a finite number of rectangles. We're doing an infinite number of rectangles. And what's the difference between doing a finite and infinite? What is the infinite versus the finite?
Infinite gives you exact.
Infinite gives you the exact area under the curve. That's right. So if you did Riemann sum, left endpoint, right endpoint, midpoint, and you did a number of rectangles approaching infinity, now you're getting the actual area under the curve. Now look at this. So you got k equals 1 to n of x of c sub k. So this is your constant, whatever endpoint, left endpoint, right endpoint, or midpoint. This is what rectangle you're on. First rectangle, second rectangle, third rectangle. And they sometimes do delta x sub k. And the reason they do delta x sub k is because the widths might not always be equal. Now, if they just do delta x, we're making the assumption that the widths are always what? But if technically it should be delta x sub k, because have we seen it where the widths aren't equal?
Yes.
Yeah, we did on Friday. We saw it where the widths were equal, and we had to actually go width times height plus width times height plus width times height. But if the width is equal, what were we able to do with the width? Put it all the way out front. Okay? Now, if the number of rectangles is approaching infinity, does it matter if widths are equal or not equal? No, because what's going to happen to the widths no matter what as the number of rectangles goes to infinity? The partitions approach 0. The widths approach 0. Partitions are widths. Okay, interchangeable. Okay, those will approach 0. All right, so let's do an example. Here we go. Let's start setting these babies up. All right, so go back to page, writing a Riemann sum in summation notation. So this is all Blake's got to be able to do. Blake's got to be able to take it and write it using this summation notation. So he's going to write, so watch carefully. He's going to write the summation from k equals 1 to n of f of c sub k times delta x sub k. He's got to be able to write this notation. All right? We already know how to write the integral notation. So we'll start with that. Okay? So, for function y equals the square root of x, I'm going to review common graphs. Don't worry, in the month of April, sometime about halfway through, I'm going to review all your common graphs, because Hunter's going to want to know his common graphs for his AP exam. And Hunter's got his common graphs down. Would you have had a hard time remembering the square root of x is the shooting star?
No.
I don't know. I think most of you got it. That's a favorite one of theirs. Okay? Draw rectangles forming right-hand sums. So we're doing an RRAM. We're doing an R. There we go. We're doing an RRAM. You good? With how many with equal subdivisions? I'm good. With equal subdivisions, which means the widths are going to be what? How do we calculate width? Let's do that right away. How do we calculate width? B minus A over N. You need to know that for the exam. It's the width of the interval divided by N. So it's clear we're going from A to B, which in this problem, they want my A to B from what? From where? 1 to 4. That's it right there, from 1 to 4. They give us that. That's given. It'll be given. So if I want to find the width, it's going to be delta x is going to be 4 minus 1 over 6. So we're going to have 3 over 6. So what's the width of our rectangles? The width is 1/2.
3 over 6. Oh.
Okay?
She's gone.
You're good. All right. And they've already got it set up really nice for us. That's kind of nice. Okay? I'm not going to even look at Gene's goal. Okay? Gene likes to break this up. We're going to set it up. Okay? So, whoa. Okay? That was crazy. But anyways, does everybody agree this is height times width? Which height times width, will that not calculate area? Will that not calculate the area of whatever triangle? She calls this A sub k, or A of k. But A of k is found by taking the height times the what? Width. We got to take the height times the width. All right. All right, we're doing a right hand. So here we go. If you need to draw one to see it. Okay? So I'm going to draw one rectangle. So I've got from 1 to 1.5. Does everybody agree? So I'm going to go from a right rectangle. So I'm going to go up. The height is going to be measured from 1.5. That's the first value I'm going to use. And I'm going to go over the rectangle. So is this going to overestimate or underestimate? Over. So you can go ahead and put it's going to overestimate. It's going to overestimate. The next rectangle, if you draw it, if you want to draw all the rectangles, would look like this. The next one would be here. The next one would be here. The next one would be here. And the final one would be there. Okay? So you can see. So I'm going to start. And the first one, I didn't even draw it, did I?
You don't need that one.
Oh, I don't need that one because we're starting at 1. I did draw it. Never mind. Because it's from 1 to 4. Now, I'm going to give you something that's a little wild. Okay? I'm going to tell you how to calculate the endpoint for the C sub k. All right, C sub k. All right, are you ready? How do you adjust it so that you're going to be able to repeat this process in the sum? Well, you have to start your rectangle at your C sub 0. So you got to start it at C sub 0. Where am I starting it at? At 1. So that's going to be your C sub 0. You're not always starting at 0. So I first of all have to offset by starting it over at 1. So C sub 0 is your start value. So everybody write start. And they're going to give you this formula. She calls it, I think, A sub k. She calls it A. I call it C sub 0, but you can call it A. You can call it whatever you want. Okay? She calls it the X sub k triangle. I don't really care. I'll write it the way she writes it too. And then you're going to have to go delta X times K. Delta X times K. Now, what's that doing for you? What that's doing, it's pushing it over every rectangle. So for K equals 1, you got delta X. So you're starting at C. So you're starting at 1. And to get to the right endpoint, you got to push over the width of the rectangle. So if K equals 1, you're on your first rectangle. You're going to push over the width how many times? Once. If you go to K equals 2, you're going to push over from the width how many times to get from 1 to the second right endpoint? Twice. if you go to k equals 3, so do you realize this is just multiples of the width? So delta, remember it was like when we did trig. Remember it was plus pi k, or plus 2 pi k? So you're pushing over multiples of the width. Now this only works for a right endpoint. Does anybody know how I'd have to do this for a left endpoint? It's a little weird. This works for an RRAM. I only do RRAMs, and they typically only do RRAMs on the AP exam, but they have done an LRAM before. Does anybody know what I'd have to do to, first of all, think about it just a second. You would have your C sub k. You would do your start, or X sub k. She does X sub k, and she does a start of A, because A is A not the start of the interval. Does that make sense that she uses A? I've seen it both ways. That's why I'm writing it both ways. Okay? But if I start at 1, and I push over the width, if I do multiples of the width, but I don't want to be at the right endpoint, I need to somehow get back to the left endpoint. Does anybody know what I'd do? Nope. What'd you say? You're on the right track. You know you got to do something to push it back over. It's actually really simple. You got to subtract, not divide, and you got to subtract by what? You want to push it from the first rectangle to the 0 rectangle. So all you'd have to do is do k minus 1. So then if you do k minus 1, since k equals 1, since you always start with the first rectangle, then you go 1 minus 1, which is what? And then it doesn't move the width at all. It doesn't add the width to the first rectangle. See what I'm saying? So if I do k equals 1, this will give you what? 0, and then you don't add the width at all. So you just stay put. You stay at the k. You stay at your start value. See that? Okay? So if you're doing an LRAM, it'd be this one. But good news is they typically only do RRAM. So we're just going to do this one. We're just going to do the RRAM. Okay? So let's write this. Here's how you'd write it. So it's going to be the sum from k equals 1. Another way to do it is some students are like, can I just set my k equals 0? Could I set my summation? Could you do it that way? If you did it that way, you could use the RRAM, but you would have to let your summation start at k equals 0, and you would go from k equals 0 not to 6, but you would go to what? 5. So you could do it that way. So you could use the RRAM formula. Yeah, but anyways. All right. It doesn't work as nice. We don't have to ever do the long way to do the summation. So it doesn't, the formulas that you use, which we're not required to do, let me just make mention of why we do k equals 1, is there's some formulas that you do to actually expand the summation. They're called summation formulas from pre-calc. And there's certain formulas that you memorize. And I'm going to show you how to do it one time, and you're never going to have to do it the long way. They don't even make you do it. I just want to show you what actually looks like if you actually work this out. Okay? But the formulas, it's crazy. We got everybody here for the first time in over 4 weeks. Yeah.
No, Cash is technically still absent.
You're actually still absent, though. 20 minutes of class is an absence. Okay? So we got k equals 1 to what? To how many rectangles we done? 6. So there it is. K equals 1 to 6. All right? And it's going to be f of c sub k. All right? So when I plug this in, okay, so we're going to have f of c sub k. What is our equation here? It's root x. So it's going to be x. It's going to be just root x, or c sub k. We're just going to put root x times delta x. Now we need to figure out what delta x is. What is delta x? It's 1/2. All right? So we've got root x times 1/2. This is our equation. Okay? Now this, the height was just the function. Do you see that? And delta x we found with b minus a over what? N. Would this not calculate the area under the curve?
It would.
Yeah, because you'd plug in the first rectangle, find the first height. You'd plug in 1. So square root of 1 would be what? 1. Let's go over there and see if that's the height of the first rectangle. Wait a second. My first height is at what? 2. So this is where you need the formula to figure out what to plug in for root x. So when I do my root x, I need to use my start value, which is going to be that little formula here, which we're going to use to calculate RAM. So to figure out that C sub k, you have to do that start plus delta x times k. So here we go. So what I'm plugging in here for the height every time to get it to be an RAM is that x sub k. So it's your start plus delta x times k. What's my start value at? 1 plus, what's delta x? 1/2 k. Here it is. That's what you plug into delta x. That's what you're going to plug into the square root of x. So it's going to be 1, it'll be the square root of 1 plus 1/2 k. And that's why when you were looking at these last night, they probably looked really weird and you probably just guessed on it. And it was like, how did they get a k in there? That's where that comes from, that a plus delta xk. And there it is. This is all you have to be able to do. You don't have to expand it or anything. You just got to find the multiple choice question that makes it look like that. All right, let's do some examples here with this. We're going to do a couple. Here's some multiple choice one that does it. So she gives you some steps. Okay, so here's a summary of the procedure. First of all, find delta x. That's the most important part. You can't do this. You can't write it as a summation without knowing what delta x is. Then find your x sub k or your c sub k, which is always going to be start. Everybody say it with me. What is it? Start plus what? Delta xk. Then, to figure out the area of the kth rectangle, your formula is always width times height. Your width is delta x, and then your height will be f of x sub k. You'll take that x sub k, plug it into the function, put the summation in front of it, and then she did the left ones. If you want to do the left ones, you can start it at 0 and then change this to n minus 1. So instead of going from 6 rectangles from 1 to 6, you can go from 0 to what? 5. Okay, that's how she deals with the left. The other way, way I was taught to do it, because I had to do it the long way, is I was taught you actually change your x sub k. You go start plus delta x at k minus 1, and then I don't have to change my k start to 1. I can leave my k start at, I don't have to change my k start to 0. I can leave my k start at 1. But we'll do it the way she does it, because that's the way they do it on the AP exam. Yeah?
Would you leave it the same for like a midpoint?
Midpoint, they don't ever have you do with a Riemann, with a summation. They're only going to have you do a left LRAM or an MRAM. If they did do a midpoint, I've never seen them do it, then you would have to do like an average for the K.
I'll just guess.
Yeah. So I've never seen them do an MRAM on.
Okay.
It is possible to do an MRAM. All right, here we go. So let's look at it. So this is all they give you. This is an actual multiple choice question on the AP exam. And this is probably the one you looked at last night and were like, yeah, I don't know. I just circled an answer.
Yep, C.
Okay? Yep, you probably circled C. It's not actually hard to do. All right, look at it. They did all K equals, this would be right here if you did a midpoint.
I see, yeah.
You see it?
Yeah.
Okay, so they did K equals 1, K equals 0.5, K equals 1, K equals 1. Well, first of all, let's go over here. What are they doing, a right endpoint or a left endpoint? They're doing a right, so you can rule out which ones? B and D. You can rule out B and D. Why can I rule out B? Because that's if you wanted to do a what? Midpoint. This would be if you wanted to do a left endpoint. Okay, so these are the right endpoint ones. Now, the next thing you need to do, I can go ahead and rule out A right now, because the formula has to be the height. Actually, no, they've got it in parentheses. I got to be careful. Okay? All right, be careful. You got to go height times width. They might actually simplify it. So I'm going to go through the process here of showing height times width, even though I think the answer's C. Okay? So first of all, I'm going to find the width of each one of my rectangles. How do you do width? B minus A over what? Now, most of you can just look at it down there and see what the width is. But let's go through the process. What is the B? 4. What is the A?
1.
So it's going to be 4 minus 1 over, how many rectangles are there? There's 6. So we're going to get 3 over 6 again, which is what? 1/2. Yeah, 2/3. So it's times a half. So here we go. We got my summation from k equals 1 to 6 rectangles. We're going to have our f of x sub k times my delta x. What is delta x in this problem? 1/2. They called it 0.5. There's the 0.5. Seems like the answer C, but they might distribute it. So let's just make sure that the answer is not A, because they might distribute the 1/2.
The insides are the same, so they wouldn't have.
Okay, hold on. Now we're going to take f of x sub k. I need to know what x sub k is. How do you find the x sub k? Start plus what? Delta x times k. What is my start value? 1 plus, what's delta x? So it'd be 1/2 k. So I'm going to take and plug that into the function. What is the function? They didn't give me the function. Okay, this is actually, it's actually what's called a logistics curve. I will show you this one later, don't worry. I happen to know what this one is, but you don't. It ends up being 2 over, you can kind of see it here. And it's shifted up 3, I believe. It's a graph shifted up 3. It's actually part of a boomerang. Do you see it? Do you see the graph shifted up 3? It has a horizontal asymptote. Okay, it's a boomerang shifted up 3. So you have the plus 3. Does everybody see that? Okay, and it actually has a stretch factor of 2. Now, you wouldn't be required to find that. You just know it's a stretch factor of 2 because they all have a 2 on top. And I need the one that when you plug in, it's usually 1 over x. But what did I plug in for my x? 1 plus 1/2 k. So that's why you got the 1 plus 1/2 k on bottom. So the answer has to be what? Because they forgot to multiply by the what? They forgot to multiply by the width. You have to have height times width. They only have, in the part A, they only have the height. Just doing the summation of the height doesn't find the area of the Riemann sum. You have to have height times width. Okay? Now, going the other way is actually easier, and it's the more preferred way on the AP exam. Usually they give you the summation, and they want you to put it back as an integral. All right? So watch. A definite integral represents the area under the curve. Last thing today. Okay, area under the curve of the function, and a Riemann sum gives us the approximation for that area. Okay, listen up, guys. Imagine that we could create an infinite number of partition rectangles in the Riemann sum. The approximation would get closer to the actual area as the subintervals of the Riemann sum increased. We actually can't take a Riemann sum with infinite rectangles, but we can do the limit, and we can take the limit of it, and we can use limit rules that we've learned to find the limit of a function to see what it would be if you could actually let the area approach infinity with a number of rectangles being infinity. Okay? So as n approaches infinity, our summation is our summation because infinity isn't a real number, but do we know how to do the limit as n approaches infinity? Yes. We've got rules for that. Okay, if it's a polynomial, we always behave according to the highest power. If it's a fraction, we compare if it's top heavy, bottom heavy, or same power on top and bottom, which is ratio of the coefficients. So we know how to do the limit as n approaches infinity, do we not? Yeah. Okay, so we can use limits if we want to do something to infinity. So here's what it looks like. For right Riemann sums, okay, you would have b minus 8. Here's your width. If it's equal width, notice if it's equal width, where can we put the width? All the way out front. And then you take and add up all the what? The heights. The y values for the function end up being the heights. Okay? Now, what that looks like is written in summation notation. It's the definite integral from a to b of f of x dx. It'd be the limit as n approaches infinity of k equals 1 to n of f of x sub k times delta x. We're going to take it from this back to this, and I'm going to show you how to do that right now. It's actually the easier way to do it. Okay? So, definition of a definite integral. The definite integral of a continuous function. Why does the function need to be continuous? Tell me. No what? No leaky area. It's got to be closed off so our dog don't run away. Okay? Because if you have a part of the fence that's closed off, the dog's going to go off, and here we go, old Yeller. All right. Even though that poor dog died. All right. So the definite integral of a continuous function f of x over the interval from a to b, denoted by the definite integral from a to b of f of x dx, is the limit of a Riemann sum as the number of subdivision approaches what? So there it is. Where x sub k is our start plus delta xk, and delta x is equal to b minus a over n. So, given the graph, okay, let's write it as a Riemann sum, and then let's go in reverse. I want you to try right now to do what we just did in that last example with no multiple choice. Write this as a right Riemann sum using sigma notation. Now, I don't want the approximate area, so here's what I'm looking for. I'm going to have the area from 0 to 4 of 1/2. Actually, they do. They want 8 rectangles. Sorry, we are approximating. So we're doing 8 rectangles. So we got 1/2 x squared plus 1. And I want an approximation written as a Riemann sum using sigma notation. So step 1, find the width of the rectangle. Step 2, find your a sub k or x sub k. So you need to find two things. You need to find delta x and you need to find x sub k. So let's see if you can get this one. And this is part of a parabola, and we're finding the area under the part of a parabola from 0 to 4. Okay, this parabola is shifted up one. It's it's vertically stretched by 1/2, so notice it's up 1, right 2.
What's the equation for x sub k again?
You got to tell me. It's on the previous page.
X sub 0?
No, x sub k. What is x sub k equation?
No, I'm saying x sub 0 plus delta x times k.
Or we'll go, she uses a plus delta xk, so that's what we'll do. Because then we know x sub 0 is the a value where you start your interval.
Oh, I see.
Got it? And delta x is b minus a over n. All right, what'd you find for delta x?
1/2.
It's 1/2 again. Okay? So it's 4 minus 1 over, are you sure it's 1/2? Hold on a second. Or it's 0 minus 4, sorry. And I can see my 4 minus 0, and I can see my a to b. Okay, so here's my a, here's my b in my integral notation. So I know the integral is from 0 to 4, not 1 to 4 this time, from 0 to 4. So it's going to be 4 minus 0 over how many rectangles? 8. So it's 4 over 8, which is what? 1/2. So it is 1/2 again. So here we go. We're going to have we're doing 8 rectangles, so don't do the limit as n approaches infinity. If they did not give you a number of rectangles to go, then put n approaches infinity. You would go limit as n approaches infinity. But since we're doing 8 rectangles, it is truly an approximation. It's not the actual area. So here we go. We got the summation from k equals 1 to what?
0.
You gotta start at 0, k equals 0, don't you?
From k equals 1 to what? 8. From the first rectangle to the 8th rectangle. You can only do k equals 0 if you're doing a what? Left. And then you do k equals 0 to 7. Okay, if you're doing a right, you do k equals 1 to 8. All right? And then we're going to have f of x sub k times delta x. Do we know delta x? So we already know that. So you could go ahead and put the 1/2 in. So we got k equals 1 to 8 times, it's going to be times 1/2 back here at the end. Now f of x sub k. I need to figure out what x sub k is. I'm going to write that right here. X sub k. I need my start. Where does it start at? 0 plus delta x. What's delta x? Do you see why you got to find delta x first? You got to find delta x first. So it's 1/2 k. Do you need the 0? Do you need the 0?
Is it 0 or is it 1?
Nope, where did my integral start at? 0 to 4. And you know that because when you look at the integral over here, it starts at 0 and goes to 4. Okay? All right? Do I need the 0, class? No. So can I just plug 1/2 k in? Where do I plug the 1/2 k in? Into the function. I plug it into the function. So you're going to have, ready? It's going to be 1/2 times 1/2 k squared plus 1. There's my height. Now, I have known them to do this on the AP exam. They will simplify this inside a little bit. So what is 1/2 k when you square it?
1/4 k squared.
Then you multiply that by half, and it's really what?
1/2.
So it might be that they have this answer in the multiple choice. K equals 1 to 8 of 1/8 k squared plus 1 times a half. And there's my Riemann sum. And then they will also do this because you could also distribute the half. But what they might do is because this is a constant multiple, and not only is this true for limits, not only is it true for derivatives, not only is it true for integrals, but it's also true, you should have learned this in a previous course, but I'm going to assume you did not learn it in AP Calc or Pre-Calc. Constant multiple works for sigma too. Where could you put the 1/2?
All the way out front.
You could put the 1/2 in front of the sigma notation. And if they do put, because it's a constant multiple, everybody say it's a constant what? You could put the 1/2 where? It goes through limits, it goes through sigmas, it goes through integrals, and it goes through derivatives. Okay, we've seen the constant multiple a tons of times. So you could put the 1/2 out front. That's all you have to do. They're not going to go much further than that. I would doubt they would distribute that 1/2. I doubt they would distribute that 1/2. Now, can we go the other way? Okay, real quick. Use your calculator to evaluate the definite integral. Use your calculator to evaluate the definite integral. Can somebody remind me how to use your calculator? Math 9 or 9er? Okay, go. Right now. I need everybody practicing the calculator when I tell you to practice it. Everybody should be grabbing a calculator every day when you come into this class.
If you don't, what are you doing?
What are you doing? Math 9 or 9er? What do you get when you math 9 or 9er?
2.5.
What is it? And which is 5/2 if you math frac it. Okay? If you math frac it and it stays a decimal, then they're going to have you rounded on the AP exam to how many decimal places? 3. 3 is the minimum. You can go to 4. You see 3 or 4, but 3 is the minimum. If you see the multiple choice and they have 4, then go to 4. If you see the multiple choice they have 3, on the free response, do 3. Okay? When should you round though? At the end. So if you're using a decimal in the problem to do something else, should you round yet? No, you should copy down every decimal that gives it on the calculator. And don't round till the very end. Okay? Don't round till the very end. All right. Here we go. Let's just go through these steps again. All right. So if you want to find the corresponding Riemann sum for this definite integral, this is a little cheat sheet for you. You find the width, which is b minus a over what? This is just a little cheat sheet. So in this problem, what would it be? So this is your a right here. This is your b. A is your lower limit of integration. B is your upper limit of integration. Sometimes called the lower bound, upper bound. Lower limit of integration, upper limit of integration. Here's the lower one. Here's the upper one. It's obvious why it's called upper. It's obvious why it's called lower. One's lower, one's upper. All right, so it would be 2 minus 1 over n. So it would be, if they don't give you a number of rectangles to do, what do? You're just going to leave it as n. So it's going to be 1 over n because we're going to let n approach what? Infinity. So what would x sub k be? Well, that's a plus delta x k. So what would it be in this problem? What's my a value? 1 plus, what's delta x? 1 over n times k, which a lot of people, most mathematicians write 1 plus k over n. So there's my x sub k. So then f of x sub k would be, what's the equation? X plus 1. So it would be 1 plus k over n plus what? 1. Because I plugged into the equation. The equation, f of x, was x plus 1. How did I know where my equation was? It's what I took the integral of. Remember, it's height times width. Width is dx in my definite integral. The equation is my height. That's my f of x equation. So I plugged in my 1 plus k over n into this equation, and I got 1 plus k over n plus 1. So somebody tell me what the corresponding Riemann sum would be for the exact area under the curve. So first of all, what do you have to start with out front, since we're not doing a specific number of rectangles? You'd have the limit as n approaches what? Infinity. You'd have your summation from k equals 1 to what? N, because we're doing a right Riemann sum. We did a right. You could have done a left. How do you write this? So it'd be the function. Now, can you simplify that function a little bit?
Yes,
Can I just make it 2 plus k over n?
I guess.
Sure you can. Times what? The width. What's the width? Now, 1 over n is a constant. 1 over n is a constant. Where might they put the 1 over n? They might put the 1 over n all the way out front. But this is the Riemann sum. There you go. Now, evaluate your Riemann sum on your calculator. Your calculator actually does a Riemann sum. Okay? There is a way to do a summation on your calculator. All right?
You know, like math,
Does anybody know where it's at?
math 0?
It's math 0 to do the summation sigma. Is that correct?
Yes.
Yeah. But if you wanted to do the limit as n approaches infinity, what would you have to do?
Put a big number in.
You would have to graph it into y1. You would have to graph this right here into y1. Okay? You'd have to put that into y1 and then go to your table and let n approaches infinity. So what did I say is acceptable? How many zeros? So you'd want to go to the table to what number? How many zeros? When you're approaching infinity, how many zeros do you need? At least 3. So you need to go to at least 1,000 rectangles. Okay, so you need to go to at least 1,000 rectangles to see what it would be. Now, they don't make you do this because if you can do this, can you not just do this over here? Can you not just math 9 and 9 it? It's way easier just to math 9 it. Okay? All right, what about going the other way? Let's go the other way real quick. Yep, let me do one where you go the other way. Okay, go the other way. Let's say I give you this. How would you write the integral?
The integral symbol.
All right, so you're going to do the integral symbol. Everybody's like, okay, I can do the integral symbol. Last one. We're cooking. What is the width? What is delta x here? Do you know that delta x is b minus a over n? Do you know that, right? So if they've got it's 5 over n, you see that? Okay, now look, you got to be careful here. What did they obviously plug into the function? There's my x sub k. Do you see that? So you should be able to figure out where it started at. So they have 5k over n, and they have a minus 2. So where did it actually start at?
-2?
It started at -2. So it went from -2, and the width of it's what? 5. So it's going to have to go from -2 to what? -2 to what? 3. Because that's a width of 5, is it not?
I mean, I guess.
Is that your b minus a?
No math.
All right. Now, what's the function's easy. What is the function? What did they plug in? So what's the function? Come on, it's easy.
5x minus 1.
There you go. 5x minus 1 dx. Done. That's it.
We're done.
That's cool. That's what the sigma is, right. Here's what I want you to do. Okay, I want you to try example 6, example 7, example 8, and then I'll finish these up tomorrow, and then we'll start the next section. Like I said, this is all for one problem on the multiple choice.